lined up together, right? They're going to hit the active elements all at the same time, right? Our solid orange line represents our line connecting those electrical signals. You good, Pat?
I'm good.
Okay, I'm coming to you. You finna understand in 1 second, okay? Then a line perpendicular to that, right? 90 degrees, because that little symbol right there means 90 degrees, right? That's the direction that our beam is going to be steered in, okay? That beam isn't steered, actually. It's going straight down, okay? The slope is what's going to determine if the beam is steered or not. Look at that, like in algebra, like in calculus. See, these electrical spikes are created with a slope, right? See that slope? That's what's going to create steering. Okay? So, again, let's do our middle one. Beam steering right here. There's our orange line right there. Matching up all our electrical signals. Okay? I make a line 90 degrees to that. Now I can see that my beam is being steered to the left. Right? So I need to draw a line first that's going to match up all my electrical signals. Draw a straight line by connecting the dots. Old school. Connect those dots from all those electrical signals. Okay? And I can see here that this beam is being steered to the left. Okay? Opposite over here. I'm going to do the same thing. Draw a straight line connecting those electrical signals like that. Everybody got that? We're good on drawing that line? Okay? Then 90 degrees to that line, I'm making another line. And that's going to determine the direction that beam is being steered. Okay? Mr. Seal, we good there?
Yeah.
Okay? Again, guys, remember, the beam is steered if the spike line has a slope in it. Okay? The beam is steered if the electrical signals coming to the elements has a slope. Okay? That means it's being steered. Okay? Remember that technique to determine which way the beam is being steered. Okay? Because I think last year I just taught them how to eyeball it. I didn't even use the book on that part. Okay, so beam steering in a linear phase array, guys, very sophisticated technology, right? Imagine 100 to 300 single channels for this little bitty transducer that this big, right? That's very sophisticated equipment. Each electrical pattern is slightly different than the pattern before it, right? Because it needs to go from this direction to this direction to this direction, right? So look at all our electrical signal patterns. They're all going to be different. Okay, that doesn't mean it goes straight 45 degrees to straight down to 45 degrees the other way. That means it's sweeping this way. It's going to continue sweeping. So from here, it may just be a smaller angle, a smaller slope, a less steep slope to get it from this right here to this right here. A less steep slope, right? We good there, Gwen? Okay. The slight variations of the slope of the spike pattern steer or sweep that beam in slightly different directions, creating that sector or fan-shaped image. Okay? So even though this is a linear transducer, the way that the electrical signals are hitting those active elements is what's creating that fan or sector-shaped image. Okay? Beam steering is achieved electronically without any moving parts, right? Because the electrical signals being sent to the active elements are coming in nanoseconds apart from each other. Okay? All of them are being fired upon to create a single sound beam. Okay? The electronics within the ultrasound system that create these patterns, guys, that's called the beamformer. Again, that's not part of the transducer. That's part of the system electronics. Okay? That's the part we're going to talk about that creates the beam. Okay? It sends the electrical patterns out in these different times to create that sound beam. Okay? And we're going to talk about all the different parts of the actual ultrasound system next semester. The pulsar, the beamformer, the receiver, different functions of the receiver. Okay? I'm almost done, guys. So, beam steering, okay? Again, quick recap. When the spike is a straight line, an unfocused beam is created. All right, guys? So, look here. It's a straight line, right? Our beam right here, this is unsteered and unfocused, right? Because it's going straight down. It's not being steered or focused. Okay? But right here, we have we have steering because it has a slope on it, right? We have steering because it has a slope, but it's in a straight line, so it doesn't have focusing. What creates focusing, guys? Y'all should already know this.
Polarization.
What creates that? The curvature, right? It has to have a curve. So that's why I said this is a straight line. It's not going to be focused, right? Because think of it. What creates focus on a conventional mechanical transducer? I mean, the internal, external. What's in common about those? It's going to be a curved active element or the curved acoustic lens, right?
Mm-hmm.
That's what's going to create focusing. No difference here. If we curve these electrical signals, then we're going to create focusing in this beam.
But it's not curved because it's straight.
Exactly. That's why it's not, see, it's not focused. Okay? Again, when the spike pattern is in a straight line, an unfocused beam is created. Yeah, it's steered, but it's not focused. Yeah, it's steered here, but it's not focused. Okay?
So what would this transducer
So how does
be
the
used
focus
for?
end up being on it?
This transducer is a regular transducer. I'm building you up to two focusing. I'm building you up to focusing. This is a regular transducer, but I'm just giving you the basics right now, so you can understand that for us to have a steered beam, it has to have a slope on the electrical signals. For us to have a focused beam, it has to be a curve to those electrical signals. Okay. What was your question, Pat?
I thought like if it's not focused, if you want to focus conventional, if you want to add a lens or something on it.
That's a conventional. Right now we're talking about electronic focus.
Okay.
Right? Because the linear phase array has electronic focus.
But here there is a curvature in the.
It's no curvature. This is a straight line. These
No,
electrical
I mean,
signals are in a straight line.
I mean
That's the face of the transducer.
Yeah.
That's just the face of the transducer.
You
That's
don't
just for
need-
illustration purposes. Don't get caught up in that.
Complex.
That's just for illustration purposes. Okay? Don't think too hard about that. We're talking about the electrical signals right now. Don't go beyond that. That's all we're talking about right now, Mr. Sale. Electrical signals. If the electrical signals are in a straight line, the beam will not be focused. Okay? All right? So, how does the pattern, and guys, I'm not gonna end right here, I'm gonna end on focusing, and then I'm gonna let you guys go. Okay. So, how does the pattern of electrical spikes, or I'm gonna end on linear phase array, then I'm gonna let you go. How does the pattern of electrical spikes from the beamformer focus the beam during transmission? Again, guys, notice it says during transmission. So what does that tell you? That focusing can also occur during reception. Okay? It's specific right here. It's telling you transmit focusing. Read my headers, transmit focusing. Okay? We know all about transmit focus because that's all we've been talking about. Okay? What are our three types of focusing?
External, internal,
And electronic, phased array. Electronic focusing, right? Internal, external, phased array focusing. Never gonna let you forget these things, guys. I'm never gonna let you forget. Okay? So, the curved pattern creates a focused beam during transmission. So what creates a steered beam? The slope. The slope. The curved pattern is what creates the focused beam. Think about in our acoustic lens curve like this, in our PZT curve on a mechanical transducer, right? So same thing. The electrical spikes are also going to be in a curved shape. That's going to create a focused beam for us. Okay? The outer crystals are going to be excited earlier than the inner crystals, right? These outer crystals are closer to the active elements than these inner crystals. They're going to be excited at a later time. Mind you, again, these excitations are happening nanoseconds apart. Okay? Nanoseconds apart. All right? So, since there is no predominant slope on this pattern, we're in like a perfect curvature right there. There's no slope on this pattern. The beam is going to be directed straight down. Okay? So this beam right here is not steered, but it's just focused. Right? See, now our beam has a waist on it, right? But it's still going straight down. Okay? So this beam isn't steered, but it is focused now because the curvature is what creates, the curvature is what creates that focus. Okay? So, Notice right here, compared to this image, compare this image right here to this image. Notice how steep or more severe our curvature pattern is than the previous image. That's going to determine our focal depth. Okay? The beam is created by this more curved electrical pattern will have a shallower focus. I would say the further away the curvature is, the shallower the focus. The closer to the active elements that the electronic signals are hitting the beam, hitting the elements at a curvature, the deeper the focus. Okay? The beam still doesn't have a slope on it though, right? It's still like in a perfect U shape, right?
Right.
Perfect U shape. So this beam is still going to be directed straight down. Okay? Do I have an image? So here we go right here, guys. Our image is side by side with our deep focus right here because our electronic signals are closer to the active elements. Okay? When the electrical signals are further away from the active elements, okay, we're going to produce a shallower focus. Meaning, look at the image. Look how close our focus is to our transducer. Right here. Look how deep our focus is from the transducer. Okay? We good there? So on our deep focus, guys, a focused, unsteered sound beam is created by this electrical pattern from the beamformer of a phased array system. Remember, our beamformer is what's sending out the electrical signals to the transducer. Okay? To let it know when to excite these active elements at these different nanoseconds apart. I know it's a lot. That's why, you know, I'm gonna, after we get through this electronic focusing and steering. Remember, I told you guys, y'all wanted me to talk about it a few chapters ago. I told you it's in depth. I can't lightly touch it. When we get on it, I have to be all in. Okay. So, you got your picture? You got your picture?
Yeah. Thank you.
But that's in your book too.
Yeah.
All right. So, guys, notice right now, our electrical signals, they have a curvature and they have a slight slope to them. Y'all see that slope?
Mm-hmm.
It's not in unison. These outer elements aren't hitting. See how these are all hitting the outer elements are going to be hit at the same time? These outer elements aren't going to hit at the same time. So it has a slope and it has a curvature to that beam. Okay? So these beams up here that are being illustrated, they're going to be focused and steered. Okay? Same thing applies. Okay? Different phasing pattern that steers the beam, focus it during transmission. Again, we're only talking about transmission right now. Transmit focusing. Okay? The electrical spike pattern is curved, creating a focused beam. It's curved, creating a focused beam. Okay? The electrical spike pattern is also sloped, creating a steered beam. That same kind of rule can still apply if you want to know which way it's being steered, right? So with this one, if I draw a straight line from here to here, right? That's going to give me a line like that. I draw a line perpendicular to that, and I know which way this beam is being steered. Okay? You can use that same rule, just use the outside elements in this case. Okay? So, again, recap that, guys. Recap that. So, steering is accomplished by the slope of the electrical spikes. Okay? Focusing is accomplished by the curvature of the electrical spikes. All right? So, last one on transmit focusing, guys. Let's talk about this. The way this beam, these electrical spikes are hitting this active element. Okay? So, this figure right here, figure 1215, shows a completely different phasing pattern. Total opposite, right, than what we've been looking at so far. Okay? The electrical pattern now is convex, right? It's shaped outwardly, right? It's shaped outwardly, right? Same shape as this, convex, okay? Or a D shape. A D shape right there. This creates a defocused or unfocused beam. Okay? Notice that this beam right here, look at this beam. This beam is doing what, guys? I want one word. Diverging, guys. That's what I want to hear. That beam is diverging as soon as it comes out of the tree. You said it?
I said fanning out.
One word. That's true too, but I want to hear that word diverging. This beam is diverging from the time it comes from the transducer all the way out. Okay? That's called a defocused beam right there. This has nothing to do with clinical imaging, has nothing to do with diagnostic imaging. It just has to do with academic interest. Okay? So if you see a beam that a spike pattern that's inverted like that, just know that that's a defocused beam. Okay? And that beam is going to diverge the whole time. Okay? Kind of like flashlights, they do that, right? Flashlights just kind of diverge all the way out, right? They don't work like a focus, right? They don't have a waist. They don't come in. They don't converge and diverge. They just kind of like this, or your headlights on your car, right? So again, guys, electronal curvature, beam focusing. Okay, electronic slope, beam steering. Okay. I think I got two things. I got transmit, still on transmit focus, we're talking about multiple focus, then I have dynamic receive focus. Then we're done. Alright? So, how does a phased array system create images with multiple focuses? Simple, guys. It's going to send multiple sound beams down each scan line. However many focuses you have. So apparently, just looking at this one, 3 focuses, right? These are 3 different colors. Okay? Each electrical spike pattern has a different degree of curvature. Of course, that's how we create focusing, right? So the first one, may have, the green one is shallow. It's shallow. It may have a steep curvature, right? And I'm going all out the colors. The red one is an intermediate. It may have a more intermediate curvature, right? From the spike pattern. Say this is my spike pattern right there. These are my active elements. And then we have the last one, the green one, and I had all these colors and I did it wrong. It's gonna create a deeper focus, right? Because that curvature is what's gonna determine the focal depths. Okay? So the pattern with the least curve produces the beam with the deepest focus. Okay? So this green one is going to be produced by the one with the deepest focus. All right. Each line in that image is created by the focal zones of those pulses, meaning that the image is going to only be created by the information created from that focal depth. It's not going to just sum all that information up. It's going to take this information from the steep curvature one, and that's going to be our sound that is from the shallow focus. Okay, so this green one is going to be represented on here with the blue. That's going to be all our image information from the shallow focus. Okay, and this blue one right here is going to be represented by the green with the deep focus. Okay. Okay. So let's talk about last thing, guys. Dynamic receive focusing. Can phase delays be used to focus a beam during reception? Of course it can. Yes, it can. Yes, it can. Focusing may also occur during reception. During reception, when the reflected sound waves arrive at the transducer, multiple neighboring elements in the probe are excited. Okay? These elements create electrical signals that return to the system's receiver via multiple channels. Okay? Dynamic receive focusing works and creates a more accurate image. And when the ultrasound system receives variable time delays, some of these electrical signals occur during reception, meaning that the image, we know that the electrical signals aren't being sent out at exactly the same time. So when they come back, these time delays are also applied during reception. Okay, that happens automatically. We don't control the dynamic receive focusing, or it's called dynamic focusing. Okay, the optimal time delays used during receive focusing depend upon the depth at which the reflection was created. Okay? I'm not going to get too in depth on dynamic receive focus. I want you to know that yes, it's possible to focus the beam during reception. Okay. Therefore, the delay patterns during receive focusing change continuously as the transducer listens for reflections. Okay. It's gonna change those delay patterns as those electrical signals come back from the active elements, right? Because those active elements are going to be vibrated at different times, right? Those vibrations are going to create an electrical signal, which is going to be sent to the ultrasound system. Okay? The ultrasound system isn't just going to process them immediately. It's going to wait on the other signals, basically, and they're going to come in at nanoseconds apart, just like they were sent out. Okay? So that's why it matters. The depth matters as to where that sound is reflecting from. Okay? That also has something to do with us getting all our reflections back before it can send out the next pulse. Okay? And I know it sounds like it's happening slow, but you know this stuff is happening faster than we could imagine. Okay? With dynamic focusing, the reflected sound is focused at many depths. This differs from transmit focusing, which is limited to a single focal point, right? Because our transmit focusing just has a waist, right? Then we have another focal zone at another depth, creating another waist, okay? Dynamic receive focusing is performed automatically, meaning that we don't have to do anything for this to occur, okay? By the system, and is not controlled by the sonographer, okay? But transmit focusing is controlled by the sonographer, right? Because we can adjust our focus, we can add multiple focus and take them off, okay? But dynamic receive focus or dynamic focusing is only controlled by the machine. Okay? I'm gonna stop right there, guys. I'm gonna do a recap of linear phased array because that's our when we talk about electronic focusing and steering. Know that information because that applies to the transducers after that as well. Okay. Any questions, guys, before I let you go? We're going to start on this recap on Wednesday. Guys, remember, you guys on the ride to noon on Wednesday. We have Ms. Shepherd's class first. I think we're both going to do like an hour and 15 minutes, hour and 20 minutes or something like that. Okay. I hope we can get to how can we determine the direction that the beam is steered, basically? Okay? The beam, so this is the way the book kind of tells you to figure it out. Okay? It says it's actually a two-step approach to determine which way the beam is going to be steered. First, we need to draw a line that connects the electrical spikes. So it's our orange solid line right here, guys. We're going to draw a line right there. That's the line that connects our electrical spikes. Right there, correct? Correct? You'll understand what I mean more on the next image. Okay? Then we're going to draw another line extending out that is perpendicular to the first line, which is represented here by that dotted line. Okay? This is an easy way to determine which way the beam is being steered. Okay? So, right here, guys, how can we, again, the same question. How can we determine the direction that the sound beam will transmit? Remember that I said, because I know this is like, man, this dude is lying. Because these electrical spikes aren't going to hit these active elements at the same time, right? What is he talking about? That's not what he just said, okay? So phasing is responsible for steering the beam by altering the timing of the electrical spike patterns, exciting those elements, okay? So these electrical signals are separated by 10 billionths or 10 nanoseconds. So even though they're not hitting them at exactly the same time, 10 nanoseconds, that's a billionth of a second. That's basically at the same time, right? Okay.
Nothing.
This because I like that word. I like the word they use right there. Okay. These minuscule time differences between the many wavelengths create a single unified beam. Okay? So these time differences are known as phase delays. So meaning that this active element right here is going to get its electrical spike before this active element, right? Because we look on the wire right here, we can see that this electrical signal is a lot closer to this active element than this one is to this electrical signal, right? So they're not going to exactly hit at the exact same time. But this right here is what's going to create steering, okay? And you can see that our beam is actually being steered this way. It's still not focused though, right? Still not focused because it doesn't have a waist, but it's being steered in that direction. This steering, that's a scan line, okay? So let's apply what we just learned. We're going to draw a line that's a straight line connecting our electrical signals. Draw a straight line connecting our electrical signals right there. I can't draw on this board. So that's my straight line right there.
Mhm.
Then I'm gonna draw a line that's perpendicular to that line, 90 degrees. What's another name for 90 degrees, guys?
Perpendicular.
Azimuth.